Here's my project about finding the thermal conductivity of a steak. We'll start off with some of our assumptions. First of all, that the thermal conductivity of the steak is constant. This is mostly true at the start, but becomes less true as the steak cooks, becomes less dense. And the next assumption is that heat flux from the pan to the steak is constant, and the temperature of the pan is constant. These are both somewhat reasonable for the sake of the calculations, but this, particularly the heat flux being constant, is not true because as the thermal conductivity of the steak decreases as it cooks, the heat flux is going to decrease in a commensurate manner. Additionally, that steak is not heated by convection is another assumption. It will be a little bit, but this is negligible compared to the conduction heating. And then finally, there's no horizontal temperature gradient in the steak, basically assuming the sides of the steak from kind of the reference frame of the center of the steak is adiabatic. We just have one-dimensional heat flow here. This is a pretty reasonable assumption. Next, for the model, we're using a semi-infinite solid just because there's a small Fourier number that I'll explain later. Also, it's not capacitance because there are temperature gradients. It's not specific geometry because of the Fourier number. And the computational method would be the best one to use, but it's just not feasible here. And down here, you can see a quick diagram of the steak and the pan. You can see L, which is the length, the half length of the steak to the middle point where I'm measuring. And you can see constant flux and constant temperature of the pan there. Boundary and initial conditions. Some of these kind of I mentioned earlier already, but constant flux is kind of the main one we're going to use that's going to inform the equation for the semi-infinite solid that we're using. We also have a Dirichlet boundary condition, basically just that at the base of the steak, the temperature is constant, basically equal to the temperature of the pan. Then also the initial temperature distribution of the steak is constant throughout, and that's pretty reasonable. So for our method, we can see the steak in the top left-hand side. It's about 3.2, 3.3 centimeters tall. On the bottom left, that's the temperature probe, the meat thermometer. I've made a marking at 1.65 centimeters to show just how far I need to stick it in to get it halfway up. There's the steak on the pan. We'll see some videos of the steak actually cooking in a moment. And on the right-hand side is the timer showing how long it took the steak to cook. And so I basically just placed the steak on the pan after taking some initial measurements and measured it periodically, more so towards the end, until it got to around 122 degrees Fahrenheit when I'm just called it cooked. For the method here, you can just see me taking the initial temperature of the and around 90 degrees Fahrenheit. Here, taking the temperature of the steak as it's cooking, there's around 56 degrees Fahrenheit, and this is towards the end where it's getting to around 122 degrees Fahrenheit there on the right. And that's when I've just called it done and ended the timer. Let that finish. Great. Here's some calculations. First of all, the top left, just calculating the Fourier number, which ended up being around 0.001, so far less than 2. The top right is the semi-infinite solid equation to figure out the temperature, and basically I just plugged in all the values I had and kind of iteratively figured out what K value worked best here. And you'll see that in the code in a minute. And then just the bottom right is how I calculated the heat flux using some initial temperatures, just a known K value that I got online, and then the length. So this is the MATLAB code I used. It's kind of similar to some of the problems in Homework 7, just as I mentioned, kind of iteratively finding K, using kind of the final temperature and all of that. And so there's a plot of kind of the values of K on the right. The one closest to 0 is the one that I wanted, so I got K equals 93. And so this isn't that reasonable because the actual value is 0.49. I'll go into sources of error in a minute. But kind of my conclusion here is the steak did eventually cook. It was cooked very poorly because it ended up burning. And that basically meant that you needed to stay on the pan longer for more heat to flow through. And that was just kind of, it didn't really taste good. I ended up cooking a lot more the correct way on my own. So some sources of error here. Heat flux calculation. Wasn't really sure how to calculate in this scenario. Made some assumptions about it being constant. That was probably not correct here because it dries and burns unless heat is transferred. Also the steak warps, and so that means that it's not all the contact isn't constant, and so that decreases the heat flux as well. And measurement wasn't always exactly 16.5 millimeters, but I think really the heat flux is the bigger issue here. If I were to redo this, improving the heat flux measurement is more important. I just heat up a plate to a known temperature and then accurately measure how much heat flows into the steak from that. I'd be much more precise than assuming it's constant. Thank you.